Hello friends, welcome to all of you. So in this tutorial we are going to learn about how to add a temperature equation into the solver of the interFoam, which is a multi-phase solver. So in the last tutorial I have already tell you about how this interFoam solver algorithm works here. Okay, so if you have not watched that video, you should watch that video first and then you should come into this tutorial here. So already I talked about the mass and momentum equations. Here we are going to just focus on the temperature equation. So this is the temperature equations that we are going to solve here. Speaking of the interFoam solver, so this interFoam solver is the solver for the two immiscible phases. Okay, so since here are two kind of phases, so this properties like rho Cp and K, that is the thermal conductivity, we need to take up these two phases. Okay, and also the temperature will be, there will be common temperature, and that will be solved after the UV equation and PE equations. Okay, now if you want to calculate the thermal conductivity, we can calculate using this correlated, that is the Prandtl number, and Prandtl number is equal to the mu Cp upon K. Okay, now this, if you have idea about the open foam, so open foam generally solve for the kinematic viscosity. So this mu will be nu, that is the mu upon rho. So we will going to divide the rho in the bottom, and then there you need to apply rho multiplication at the top also. And if you do some modification, we are going to find out this correlation, that is the K equal to rho nu Cp upon Pr. And if you want to write this K in terms of the open foam, then we can write at this kind of the equations. We will come back to the equations. Let's first go to the terminal. So let's open a terminal, and let me just zoom in little bit. Okay, so I have to create the open foam environment, and let me create one folder where we are going to work on the solver and the library. Okay, so here I need to create interTemp foam of the solver and library in this folder only. Okay, so now I can go to the this this folder that I have created, and you can see here that there is currently no folder. So since we want to do modification of the interFoam solver, so we can copy that by default available solver into the current folder. Okay, for that purpose I can go to the foam app. Okay, and then solvers. Okay, so here we are going to copy from this multi-phase solvers, and that is the interFoam. Okay, so interFoam solver that we want to copy here, and this dot will be written here because we want to copy this solver into the current directory. So now you can see here that we have this interFoam solver available here. We want to develop our new solver, so we can rename this solver. Okay, so we can rename it as a interTemp foam. Okay, so this is the new solvers that we want to do modification. Okay, now we can go to the this solvers, and here currently you can see that this solvers is again still the source file is still has name interFoam, so we have to modify this also. Okay, so we can write it as a my interTemp foam.c. Okay, so this we have modified here. Okay, now we need to go to the make folder. Okay, and in the make folder there is a two file. Okay, so if I go to the make folder, so you can see here that there is a two file, that is the option and files. So if you have watched my tutorial on the solver modification, you have some idea about that what is option and files. But in simple one line I can say that files is talk about that which source file you want to compile, and option is the linkage libraries that is needed to compile the given solver. Okay, so since we have modified our solver, that is the source files as a my interTemp foam.c, so we need to modify this also. Okay, so we can go to the make and files. Okay, and here you can see here that this is still name as the interFoam.c. So since we are changing the name of our solver, we need to do modification of this also. Okay, so we need to put it as a my interFoam. Okay, so this is the required because we want to modify the solver. Okay, now after compile, we want to create a new solver, that is the my interFoam. Okay, and after compilation, we don't want to change the default app bin of the OpenFoam. Okay, so remember I told you that whatever things you want to compile, you should compile your user app bin or lib bin. So app bin is related to the solver, lib bin is related to the linkage libraries. So if you want to do any modification, you should work on your own user. Don't try to change the default installation of the OpenFoam. Okay, so we can save here. Okay, now this .c has been changed, that is also changed, and let's first compile here and let's see what error we are getting. Of course we are going to get error, and what is the error that I will show you. I just wanted to show you that error. So you can see that while we are compiling, we are getting that this library or directory or file is unavailable. So why we are getting this error? So let me show you that. So here we have created that folder, my interFoam, and if you go to the options, so if we go to the options, you can see here that these libraries are linked from the source file, library src file. Okay, but this library we need to have inside the folders, that is two folder back from the make folder. Okay, what I mean to say that we are present here, pwd we are present here, and also make is available here. So this means that if you go back, okay, so this two folder back, there should be one folder with the name of vof. Okay, so two folder back, if you go here, there should be folder with the name of foam vof. Okay, now let me show you that whether here any vof folder is present or not. Okay, so if you go to the multi-phase, here this is the interFoam, and if you go one folder back, there is a one vof folder is present. So we can copy it from here and we can paste here. Okay, now if you go to the vof, and you can see here that this create alpha flux is .h is present. Okay, so what I am trying to convey here, so see here different .h header files are available. Okay, so these .h header files and some of these .h header files are linked by using these options. Okay, so these are the linkage library that is going to used for this .h header files. Some of this .h header files like create fields.h, okay, and others are like UE equation.h and P equation.h are present here only. Okay, so you can see that UE equation, P equations, and alpha SGFP.h in it correct 5.h. So some of the .h folders are present here only, but some of the folders are linked from the given src libraries here. Okay, now you are getting error because this create alpha flux.h is not available, because this create alpha .h is not available because this should be present here, that is the vof folder. Now we have copied here, so I think this should not show error, because here you can find that create alpha flux.h is present or available. Okay, so now if I run, okay, sorry, we need to go to the folder where this wmake folder is present. Okay, so this here we are double make option is not existed, that is why we are getting this error. So we need to go to the one folder further. Okay, so now you can see here that this different available linkage library as are being compiled, and I hope that there will be no error for now. Okay, so now our interFoam is available here. We are going to add the this temperature equations. Okay, for that purpose, as I told you that we need to have the Prandtl number and this Cp and mu. Okay, so we can adopt the some models from the OpenFoam, from the transport model, and we can do the modification according to the our requirements. Okay, so if we open here, so you can see here that there is a one model present here, that is the immiscible incompressible two-phase mixture.h. So from this two-phase mixture this models, OpenFoam calculates the viscosity and density of the two phases. Okay, so we can take this immiscible incompressible two-phase mixture.h, and we can add the this Cp value and the Prandtl value, and from their Cp and Prandtl and the viscosity we can calculate the kappa of the given two immiscible fluid phases. Okay, okay. Now here you can see here that this is the library that is being called, that is the immiscible incompressible two-phase mixture. Okay, so here if we see on the .c source file, so you can see that this .h is being called here. Okay, now this .h folder when you will open, so you can see here that there is no any properties function for the properties available here. Okay, so this here you can see that here thus just the virtual functions are defined, which is going to correct the physical properties of the given two immiscible fluids. Okay, so this properties, that is a viscosity or the density, is not being called here. Okay, but when you go to the make folder and when you see the options, so you can see here that the different incompressible properties are being called from the this incompressible folder. Okay, so what I mean to say that when you go to the incompressible folder, you can see that these are the models for the viscosity, and this is the folder where these different properties are being calculated. Okay, so you can see here that this is where this density and the viscosity calculated from the different viscosity model. So this mu model 1 and mu model 2 is calculated from this different viscosity models. Okay, and this rho 1 rho 2 is calculated from the given dictionary. So what I mean to say that we have to work on this folder only. Okay, in incompressible folder we need to work on. So we can directly copy this incompressible folder and we can just write it here. Okay, so this is where we are going to work. Okay, let me do some modification into the make. Okay, we are not going to change anything to the viscosity or other models. We are also not going to change to the single phase transport model. We are just going to work on this incompressible two phase model. Okay, so let me just rename it as a my live. Okay, my live incompressible two phase mixture. Okay, so that is where we are going to work. Okay, and similarly here we have to change this to name also. Okay, here we are going to change it, and here also we are going to change it. Okay, let me open this .h folder, and wherever this incompressible two phase mixture is written, we can just change it by with your name. Okay, so you can see here that everything that has been changed here. Okay, similarly we need to change into the .c. Okay, so you can just press Ctrl.h and you can change. Okay, so this is what we have to do. Now this folder name you can also change here, and this we have already changed. So this file in make folder you need to change here, and remember I already told you that this need to be compiled in the user lib bin. Okay, so this is we have done till here. Okay, so this wmake folder just needed this incompressible.c and this folder. So we can now compile by going to this folder. So let me close this and let me open this. Okay, and we can just zoom in. Okay, so we can type of6 wclean.all and wmake. So remember, if we want to compile the library, we have to type wmake libso. Okay, so again we are getting error that this 2-phase mixture.ts folder is not present here, and now I think that you can figure out this error by yourselves. So if you go to this option folder, so you can see here that there should be means one library, that is one back folder, and this 2-phase mixture library should be also included here. Okay, what I mean to say that, so this is where this make folder is available. So if you go one folder back, this 2-phase mixture should be present here. Okay, so this is where wmake exists. So we need to come to the one back folder, and this is where 2-phase mixture folder should be present here. Okay, because it is going to ask for the this.h folder. Okay, now I can clean this, and now I can do the wmake show, and hopefully it should work now. Okay, so now this library is being compiled, and now we can do modification based on our requirements. Okay, so this is the .h folder, and this is the okay, sorry, let me just close it, then we can open it. Okay, so this is .h and this is .c where we are going to work. Okay, so first go to the .h, and here we are going to need we can copy. We are going to define this cp1 and cp2 as a dimensioned scalar like density, and similarly we are going to define Prandtl number. Okay, okay, so this is the 4 quantity that we are going to need. Viscosity is already given here, and density is also already given here. Now we want to calculate the kappa f. Okay, so similar to this viscosity, we can write it as a returned the kappa of the fluid. Okay, so here we can write, sorry, we need to take this kappa as a surface scalar field. And why we need to this as a surface scalar field, I am going to let you explain in a little bit time. So we can write it as a kappa f. Okay, so what which changes we have done, we have defined this 4 dimensioned scalar quantities, and we have defined one functions, that is the kappa f, which is the type of the surface scalar field. Okay, so this 4 changes we have done here. Okay, now, and here you can also write the, it will return the phase interpolated kappa. Okay, so now whatever the changes we have done inside the this .h folder, similar to here we have to done into the .c folder. So here you can see here that these are the variables we are protected. Okay, therefore we have to define here these variables and this is the CP1, CP2, and similarly CP2 and CP1. Okay, similarly we can define the PR1, that is the Prandtl number 1, and PR2, that is the Prandtl number 2. Okay, now we have to look up inside this properties where viscosity properties is given, and it should going to find out the CP1. Okay, similarly we have to write here CP2. Okay, so this lookup function is going to read the CP1 values from the folder of the viscosities properties folder. So generally this viscosity properties folder is given inside the transport properties folder. Okay, so in that folder it is going to look up for this CP1 and CP2 and PR1 and PR2, and it is going to assign to the this CP1 and CP2 and PR1 and PR2 variables. This is the so dimension of the CP1 can be written as the m0, length 2 and time -2 and k -1. So we can, instead of writing the density, dim density, we can write it as a dimension set. So instead of the writing dim density, we can write the dimension set, and inside that we can write the 0, 2, -2, k -1, and 0, 0, 0. Okay, so this is the dimension set of the CP1. Okay, similarly we can copy from here and we can paste here. Okay, so this is the dimension set of the CP1 and CP2. Okay, similarly we can copy here, and this Prandtl number is a dimensionless quantity, so we can write here 0, 0, 0. Okay, because it has no dimension, so all the dimension parameter will be 0. Okay, so this is how we can define these 4 parameters. Okay, now we have defined this rho1, rho2, CP1, CP2, PR1 and PR2. So we can see that how this functions is being created here. So this, similar to this rho1 and rho2, we have to find out the one return function for the viscosity, this CP1 and CP2 also. Okay, so similar to this also we can return the dimensioned scalar function for the CP1 and CP2. Okay, so it will be required when we are going to need these variables inside the solver. So we are going to call this CP1 function and CP2 functions. Whenever we are going to need these variables inside the solvers, then we are going to call this solver, and these functions, member functions of the this defined library. Okay, so when we will develop a solver, there you have idea about that why we are defining this member functions for the Prandtl's number and for the CP1 and CP2. Okay, because this CP1 and CP2 and Prandtl's number are the protected property. So if you want to call these variables CP1, CP2 or PR1 and PR2, we need to call these functions using these member functions. Okay, let me just give you more brief what I am trying to convey you. Okay, so if you open this, if you open this create folder .h, okay, and if you are going to ask for this rho1 properties, so suppose you want to get the density of the first mixture and density of the second mixture, so you can see that you are calling this member function rho1 and rho2 member function. So this row 1 and row 2 member function is being called from here only. Okay, this is the row 1 and this is row 2. So if you are trying to get these values by just calling this variables row 1 dash and row 2 dash, it is going to show you error because these are created as a protected properties. Okay, similarly if you want to call the cp1 and cp2 and pr1 and pr2, we need to call using this member functions. Okay, so you can call const dimension scalar row cp1 equal to the mixture dot cp1 or mixture dot cp2, similarly for the Prandtl's number. Okay, so now we have done for the variable. Still one thing is left, that is the kappa. So we need to define the kappa function. Okay, so let's go to this folder here, and remember we have created this kappa f using the surface as a surface scalar field. Okay, so that is why we need to define this as a surface scalar field. Okay, so here we have created as a surface scalar field, so therefore we need to define it as a surface scalar field. Okay, this is going to be remain same because we are calculating the alpha 1f. Okay, and here we need to find out the kappa f. Okay, and this variable should be changed something little bit, and let me keep it like that only, and let me just go to the formula that I was showing you on the slide, and from there you can figure it out that how we are going to calculate this kappa f. Okay, so friend, here this is the formula for the kappa f. So we are taking the row density, mu, cp and pr. Okay, so we need to calculate this kappa for the both phases, and we need to multiply with the fraction of those phases, and then we need to add up. Okay, what I mean to say that first we are calculating this k for alpha 1. So you can see here that there is a alpha 1. Okay, that is the fraction of the fluid 1. Okay, now we are multiplying with the row, that is the density of first phase, then cp1, that is the cp1 of the first phase, then this is the Prandtl number of the first phase, and then we are interpolating with the viscosity. Okay, so this is what the formula is. So I think there is some error. So this is the alpha 1, this is the row 1, this is the cp1. Okay, and this should be multiplied with the interpolated